Hey everybody, today you're going to be looking at the center of mass of different systems. The neat thing about center of mass is it's a pretty conceptual idea. It's very intuitive and there's some good math to it. It's kind of the ideal physics topic because you can talk about it and see it physically. You can have a sense of what's going on visually, and you can describe it with math and words. For this problem, my question is, where is the center of mass of these four systems? Pause the video and take some time to think about where the center of mass of these systems would be. Each of the center of masses of these systems is at the location of the star shown. For the first green rectangle, as long as it is a constant density, the center of mass would be right in the middle. And you would be told explicitly if something it has a non-constant density. But in this case, like just a regular old rectangle, center of mass will be right in the middle. If you took any regular old rectangle and tried to balance it, it would balance right in the middle. If you took a meter stick and balanced it, it would balance right at the 50 centimeter mark. For the purple system, the center of mass would again be right in the middle there. And that's okay. The center of mass doesn't have to be where any mass actually is. In the case of the yellow system with the M and 3M, the center of mass wouldn't be in the geometric center, but shifted more towards the mass of 3M, because the center of mass is going to be the average location of all the mass in a system. For something like New Jersey, that might be kind of difficult to determine. But if you actually took New Jersey and hung it from a string, it would always line up with, like, the center of the earth and the center of mass would always make a straight line with the point that you're hanging it from. Because the force of gravity always pulls down directly from the center of mass. If you click the link below New Jersey, it'll give you some information about these hanging masses and where you can always find the location of a complex mass by thinking about where that force of gravity is originating from. Finding where the center of mass of a system will really help us describe how a system moves. In the case of Newton's first law, we would always say, hey, an object that is at rest will stay at rest unless there's an unbalanced force exerted on it. When we said the word system back in October, we were introducing Newton's laws, what we meant was the center of mass of a system. In the case of this astronaut GIF, which we've seen before, even though his arms and legs might be moving, what we're describing is the center of mass of the astronaut. That is going to be at rest and stay at rest unless there's an unbalanced force exerted on it, or have a constant speed in a straight line unless there's an unbalanced force exerted on it. The center of mass is super fun to see, even for people not in a physics class. This TikTok trend is called the Center of Mass Challenge, and it involves people like leaning over, taking their head, putting it in their hands, and quickly moving their hands behind their back. Some people can do this no problem, but other people fall over. It's a neat thing to try when you're at home and have a safe cushion beneath you. The reason why certain people can do it and certain people can't is because their center of mass is either supported by their legs beneath them or not. If the center of mass, in the case of this left example, is directly above the place where the knees are in contact with the floor, they're going to be okay. But if your center of mass is further up in your body, you're going to tilt over because there's no actual support beneath your center of mass. This is the key for anyone trying to balance anywhere. And a lot of times there is a difference based upon the kind of biology that's going on inside of your body. Little children have center of masses that are around their belly button because little children kind of look like little cylinders. But in the presence of estrogen or testosterone, hips can widen or shoulders can widen. And that causes the center of mass of different people to shift. And a lot of times that can explain what's happening in the center of mass challenge. It's not true for everybody, so don't have any existential crises if you can do or not do the center of mass challenge by like bringing your hands behind your back. But it's a neat example of physics in work on TikTok. If you're into computer animation, figuring out how the center of mass like moves with a body and how that causes different people to balance is crucial to think about, and I highly recommend this link for anyone interested in animation. And there's lots of toys around that work with center of mass as well. If you find this eagle in my classroom, it'll balance right on your finger, right on the stand, because the center of mass is right at the beak. Now, for calculating the center of mass, what you need to do is realize that the center of mass like the location of it involves summing up all of the mass positions. That's this m times x, mass multiplied by position. If you multiply masses by position and add them all up for a system and divide it by the total amount of mass in a system, you'll be able to figure out where the center of mass of a system is. This case details the examples that we looked at in the do now. These calculations might look crazy right now, but let's follow them along. In this purple one here, what I'm doing is saying that the origin is at the left mass, the center of that one. That puts that mass m at a position 0. So its mass position would be 0. Mass m, position 0, so mass multiplied by position is 0. I'm going to say the second mass over here is at a position r. Could be anywhere. If I had a ruler, I could actually measure it, but I'll just say it's a position r. And it's got a mass m at position r. So its mass position is mr. The total mass position of the system is 0 plus mr, or mr, and the total mass of this system is 2m. If I simplify that, I find that this position of the center of mass is at r over 2, which is exactly what we thought in the do now when we just guessed where the center of mass was intuitively. It would be right in the middle of the system. In the yellow case, everything's the same except this mass on the right side has a mass of 3m. So the total mass position in this system is 3mr. And the total mass of this system is 4m. If I simplify this one, the position of the center of mass is 3r over 4, which is again where we thought the center of mass was. It's shifted closer to the mass of 3m. We didn't exactly have the 3r over 4 down exactly. We weren't totally sure where it would be in the do now, but the math explains our intuition in the beginning. So I love this example because it makes a ton of sense. Now you could define the origin as anywhere. You could define it as the right mass, you could put it right in the geometric center, you could put it a million miles away, and the math will always work out where you always find the same position of the center of mass. As a neat mathematical example, you can try that out and put this origin at different spots and find that you always are able to locate the center of mass in the exact same spot for a system. This next example allows you to get some practice calculating the location of the center of mass. Now in this case, it might seem crazy because it's got 5 different masses and horizontal and vertical positions, but calculating the vertical center of mass is exactly like calculating the horizontal center of mass. You just replace your x's with y's. For this one, you're going to need to choose your own origin, and that might be different from the person next to you, but you can definitely say where the center of mass is. So, pause the video, take some time and analyze where the center of mass is, and then figure that one out. If you did everything correctly, the center of mass should be at this star right here. My x equals 0 axis was right here all the way on the left side, and my y equals 0 axis was all the way on the bottom. So mine ended up being at 2.3 meters, comma 2.1 meters. You might have had a different origin, but we should both agree on where the center of mass is right at that star. And looking at the example, I don't just listen to my calculator here. I say, that makes sense. I'd expect the mass to be concentrated closer towards this 4m, closer towards these 2m's. They're the biggest masses in the system. The rest of this video deals with some good examples of projectiles flying through the air. I highly recommend, if you're into track and field, watching this video. Even if you're not in the track and field, it's a good one, about the Fosbury flop. But this presentation is everything you need to know about calculating the location of the center of mass in AP Physics 1.